Okay, we'll discuss some of the numerical problems under thermodynamics chapter. So this is question number 1. 2 moles of a gas undergoes expansion from 10 liters to 20 liters against a pressure of 2 atmosphere. Calculate the work done in this process. Okay, so what are the data given? Initial volume is 10 liters and it is expands to 20 liters, so final volume is 20 liters. It is given against a pressure of 2 atmosphere, which means the pressure remains constant during the expansion. Okay, so against a pressure means it is nothing but external pressure. So here external pressure is 2 atmosphere and it is the gas is expanding against a pressure of 2 atmosphere means gas expansion takes place at constant external pressure. So external pressure is constant. We all know that whenever external pressure is constant, okay, you can call that process as irreversible process. Okay, so how to calculate work done? You know very well the general work done formula minus integral external pressure into change in volume. The integral goes from initial volume V1 to final volume V2. Remember, this is general formula. It is applicable for both expansion as well as compression. Now, external pressure is constant, so you can keep it out, minus external pressure. Then you will get integral dV. Integral dV is, what is integral dV? Integral dV is V. Upper limit is V2, lower limit is V1. So if I substitute upper limit and lower limit, I will get V2 minus V1. Okay, this is the work done formula if external pressure is constant. Okay, now what is the external pressure given? The external pressure given here is 2 atmospheres. 2 atmospheres into final volume is 20 liters and initial volume 10 liters. Okay, so this is in liter, this is in liter, so this unit also liter. Okay, I'm just writing with unit, right? So 20 minus 10 is 10, 10 into 2, 20, so we'll get 20 liter atmosphere. Okay, this is the work done, but the general unit for work done is actually joule. So you should convert liter atmosphere into joule. How to do that? You remember this, 1 liter atmosphere equal to 101.3 joules. Remember this is very useful conversion quantity. Try to remember this. So 20 into 101.3 will give you the answer in joules. Okay, and it comes out as minus 2026 joules. Okay, this is the amount of work done when gas expands from 10 liters to 20 liters. Listen carefully. Here they did not mention whether it is ideal gas or real gas. Those informations are not necessary if the external pressure is constant. Okay, whenever external pressure is constant, then work done formula is always minus P external into V2 minus V1, right? And what does this minus sign indicate? The minus sign indicates that, okay, here work is done by the system. Expansion means work done by the system, so W should be negative. Okay, yeah. Now we'll move on to the next question. Right, this is question number 2. Just go through the question carefully. 2 moles of a van der Waals gas. 2 moles of a van der Waals gas undergoes isothermal expansion from 2 liters to 20 liters. Calculate the change in internal energy of the gas. Okay. Okay, so we know very well internal energy U is a function of temperature and volume. Okay, so if there is a change in temperature, then internal energy will change. If there is a change in volume, then internal energy will change. So I can write the change in internal energy arises either due to change in temperature, dou U by dou T, at constant volume into dt, or due to volume dou u by dou v at constant temperature into dV. So the change in internal energy arises either due to change in temperature or due to change in volume. Okay, now listen carefully. du is equal to, you know very well, dou u by dou t at constant volume is nothing but Cv. So this is Cv into dt plus dou u by dou v at constant temperature into dV. This is the general expression for change in internal energy, right, of a system. General expression. It is applicable for ideal gas, real gas, okay, solids, liquids. This is general formula. Now, in the given problem, see what is given? In the given problem, 2 moles of van der Waals gas, N is equal to 2 moles, and the gas given is van der Waals gas, undergoes isothermal expansion. Isothermal expansion means temperature is constant. Temperature constant means dt should be 0. If dt is 0, then this part becomes 0. Okay, if dt is 0, then this part becomes 0. Then undergoes expansion from 2 liters to 10 liters. So initial volume is 2 liter and final volume is 10 liter. They are asking calculate the change in internal energy. Listen, for van der Waals gas, listen, this is very important. Try to remember this. For ideal gas, dou u by dou v at constant temperature is 0, because you know very well, for ideal gas internal energy depends only on temperature. If you keep temperature constant, then there cannot be any change in internal energy. So dou u by dou v at constant temperature should be 0 for ideal gas. In the case of van der Waals gas, okay, we can derive the expression for dou u by dou v at constant temperature for van der Waals gas, but I am not going to derive it because I have already taught this how to derive it. Okay, so I am going to write the expression directly. So dou u by dou v at constant temperature. This quantity is also called as internal pressure of the gas. Internal pressure of the gas, which is equal to A n square by V square. Okay, this is the value of internal pressure for van der Waals gas. Now substitute this quantity here. So what we get, let me write here, what we get is du is equal to A n square by V square into dV. Now we need to calculate internal energy. So take the integral both sides. This is for small change. For finite change, you have to integrate. So integration of du is delta u equal to A is a constant, n square is constant, then we have integral dV by V square, initial volume V1 and final volume V2. V square, okay, dV by V square. You know, integral dV by V square is minus 1 by V. You take minus as common. So you will get 1 by V, upper limit is V2, lower limit is V2, V1. So you will get 1 by V2 minus 1 by V1. And we have minus sign in the outside. So if you multiply with the minus sign, we end up with this equation. Delta U is equal to A n square into 1 by V1 will come front minus 1 by V2. Okay, how to get this expression? You try to find out. Okay, it's a very simple one. Now, delta U is equal to A value is given. A value is 0.2. Okay, and number of moles is given. Number of moles 2 moles. So 2 square is 4 times 1 by V1. Okay, V1 is 2 liters. So 1 by 2 minus 1 by 10. Okay. So if you simplify this, you get 0.8 into make the cross multiplication and take the LCM here. So 10 minus 2 is 10 minus 2 8. So 8 by 20. Okay, 8 by 20. If you simplify this, you will get the answer as, yes, we'll get the answer as 0.32. And remember, the unit of A is atmosphere liter square per mole square. And here we have n square, now mole, right? N is mole. We have mole square. So this mole square and the mole power minus 2 cancel. And here we have 1 by volume. 1 by volume is liter inverse. So I have liter square, so liter inverse. If you cancel it, you will get 1 liter and atmosphere. So you will end up with the liter atmosphere. If you convert this into joules, what you have to do? If you want to convert this into joule, multiply this by 101.3. Okay, you will get the answer in joules. Okay, so if we multiply, we will get the answer as 32.416 joules. This is the change in internal energy of 2 moles of van der Waals gas when it undergoes isothermal expansion from 2 liters to 10 liters. Okay, and for the gas, van der Waals constant is given here. Okay, right, just go through this. Next, this is problem number 3. A real gas, 5 moles of real gas, undergoes isochoric heating from 300 Kelvin to 320 Kelvin. Calculate internal energy change in this process. Given CVM value for the gas is given and it is independent of temperature. Okay, listen, in the last question, when we discussed the last question, I gave this expression du is equal to Cv dt plus dou u by dou v at constant temperature into dV. This is general expression for internal energy. It is applicable for ideal gas, real gas, solid, liquid. Okay, for any substance you can use. Now it is given clearly that the process is isochoric heating. Okay, so what is given here? It is given that the process is isochoric. Isochoric means volume is constant. Volume constant means dV should be 0. Okay, and how many moles given here? There are 5 moles of substance given. Initial temperature is 300 Kelvin and final temperature is 320 Kelvin. Then CVM value also given, molar heat capacity at constant volume, which is 50 joule per mole per Kelvin. Okay, since it is a isochoric process, dV is 0. If dV is 0, then this part becomes 0. So what we left with is du is equal to, you know very well what is Cv? Cv is nothing but number of moles into CVM. Okay, number of moles into CVM into dt. Now integrate this. If you integrate, see du means change in internal energy for very small process, very small change. For finite change, you have to integrate. So if you integrate both sides, integral du is equal to integral n into CVM into dt. We have to integrate both sides. Integral du is nothing but delta u, and during the process, during the heating, and it is not given that gas is leaked or some extra gas is added, no, which means number of moles remains constant. So keep the n out. Then it is also given that CVM is independent of temperature. Since CVM is independent of temperature, you can also keep CVM out. Therefore, what we left is integral dt. What is the initial temperature? Initial temperature, let me take this T1, final temperature T2. Integral dt is T, upper limit T2, lower limit T1. Okay, so what we get is n into CVM into T2 minus T1. This will give you the change in internal energy of the gas. Okay, now let me substitute the values. Number of moles 5 moles, CVM value is given 50, final temperature is 320 Kelvin, initial temperature is 300 Kelvin. So what we get is 5 into 50 into 20. So if you multiply, you will get the answer in joules directly. Right, so 5 into 20 is 100, 100 into 50, you will get 5000 joules. Okay, listen, number of moles unit is mole, CVM unit is given, joule per mole per Kelvin, and here difference in temperature, it is given in Kelvin. So Kelvin inverse Kelvin cancel, mole inverse mole cancel, so that you will get the final unit as joule. Okay, so this is the change in internal energy. Okay, for the isochoric heating process. Okay, so for this given data, this is the answer, right? Just go through this. Okay, now let me move on to the next question. Question number 4. 5 moles of an ideal gas undergoes isothermal reversible expansion from 10 liters to 20 liters at 298 Kelvin. Calculate the work done in this process. Okay, so first let me write what are the data given. So 5 moles is given, so number of mole is 5, and it is given ideal gas, very important. Okay, if gas is given, just make a note of it. Okay, then it is given isothermal reversible expansion. What is isothermal? Isothermal means temperature constant. Temperature constant means dT is 0. Then it is given reversible. Reversible means external pressure is equal to the gas pressure. We normally write gas pressure as P. In this case, we have taken ideal gas, so P is equal to nRT by V. Okay, so if I substitute this in the work done formula, listen, they are asking to calculate work done. Before that, initial volume is given, V1 equal to 10 liters, final volume is 20 liters, and temperature also given 298 Kelvin. Okay, now listen carefully. External pressure is equal to gas pressure. Therefore, here, what is the general formula for work done? Work done equal to minus integral initial volume V1 to final volume V2, external pressure P external into dV. This is the general formula for work done. Now, P V1 to V2. In our case, the external pressure is given as gas, it is equal to gas pressure, and for ideal gas P is equal to nRT by V. So I will directly put this nRT by V here into dV. Number of mole, there is no leakage of gas, so number of mole is constant, R is constant, it is isothermal process, so temperature also constant, so I can keep this nRT outside the integration. So minus nRT integral V1 to V2, okay, dV by V. Integral dV by V is ln V, upper limit V2, lower limit V1, so you will get ln V2 minus ln V1. Log A minus log B can be written as log A by B. So I will write the answer directly, minus nRT ln V2 by V1. Okay, now this is in natural logarithm. We will convert into common logarithm. Base 10 is the common logarithm. So if you convert natural logarithm into base 10, you will get minus 2.303 nRT log base 10 final volume by initial volume. Okay, students, observe carefully. You need not derive all these things while doing problem. Okay, if it is possible for you to remember this formula, write the formula directly and substitute the values. Okay, I am just giving you the some additional information how to get the work done and all. If you remember the final formula, use the final formula directly and substitute the value, calculate the answer. Okay, it's very simple. So work done equal to minus 2.303, number of moles given is 5 mole, R value gas constant 8.314, temperature is 298 Kelvin, then log base 10, final volume is 20 liters, initial volume 10 liters. So this is log 2. Okay, so what we get is minus 2.303 into 5 into 8.314 into 298, and you will get log 2. The value of log 2 is 0.3010. Okay, now what will the answer? Yeah, we get the answer as minus 8587.3017 joules. Okay, if you divide this by 1000, this is in joule. If I divide this by 1000, I will get minus 8.5873 kilojoule. Okay, this is the work done, right, in the isothermal reversible expansion of 5 moles of an ideal gas from 10 liters to 20 liters at 290 Kelvin. Okay, if it is given isothermal reversible expansion or compression, use this formula directly. Try to remember this formula. You can directly write the formula and you can substitute the values and you can calculate the answer directly. You need not derive and all. Okay. Yeah. Now let me move on to the next question. Write proper thermodynamic terms for the following process. We need to write the proper term, right? So what is the name for this process? A. Process A. What is the name? Listen, it is given solid line, so it should be reversible process. Solid line, if it is given in a graph of a thermodynamic process, then it should be a reversible process. Now this is initial and this is final state. See, during this process, pressure remains constant. See, pressure remains constant, but temperature decreases. Temperature decreases means cooling. Pressure remains constant means isobar. Therefore, this process is reversible isobaric cooling. Okay, this process is the proper term, thermodynamic term, reversible isobaric cooling. Okay, now see the question B here. In question B, it is given P is plotted against V, and again it is a solid line. Okay, and it is given hyperbola. Remember, hyperbola is given. If it is hyperbola, it could be either reversible, isothermal, and here see, initial volume is small and final volume is large. Okay, volume is increasing, so it should be expansion. Reversible, it could be either reversible isothermal expansion of ideal gas, or it could also be reversible adiabatic expansion of ideal gas. For both isothermal expansion and adiabatic expansion, reversible expansion, we get hyperbola. Okay, yeah. Then question C. So what is given here? Listen, again solid line is given, so it is a reversible process. Listen, this is initial and this is final. When we move from initial to final, temperature decreasing, right? Temperature decreasing means cooling, but volume remains constant, so it is isochoric. So the process is called as reversible isochoric cooling. Reversible isochoric cooling of gas. Okay, just write cooling is enough. Then question D. See this question, again it is given solid line, so it should be a reversible process. But here temperature is, this is initial state, this is final state. Temperature is increasing means heating. During this heating process, pressure remains constant, so it is isobaric. So what's the name? The name is reversible isobaric heating of the substance. Okay, yes. Right now, let's move on to question number 6. 10 moles of an ideal gas. Let me write what are the data given directly. 10 moles, so N is equal to 10. Ideal gas is given. Note down the gas. Whenever gas is given, just note down. Undergoes isobaric heating. Isobaric means pressure is constant. Pressure constant means dP should be 0, and it is heating. Heating occurs from 310 to 340 Kelvin. So initial temperature is 310 Kelvin and final temperature is 340 Kelvin. What we have to do? Calculate the change in enthalpy of the process, and it is given that CVM value is 2R and it is independent of temperature. Okay, listen. So what to do? Listen, you know very well, in the case of enthalpy, this is the general formula. Enthalpy is a function of temperature and pressure. So change in enthalpy arises either due to temperature, dou H by dou T at constant pressure into dt, or due to change in pressure, dou H by dou P at constant temperature into dP. Okay. Now, in this case, it is given clearly isobaric, pressure is constant, so dP is 0. If dP is 0, then this term becomes 0. If this term becomes 0, then I can write dH is equal to And remember, dou H by dou T at constant pressure is nothing but Cp. So it is nothing but Cp into dt. Okay, or we can also write this as what is Cp? N into Cpm into dt, right? But okay, this is the formula, but in the given expression, in the given problem, Cpm is not given. They have given Cvm, but the gas is ideal gas. You know very well, for ideal gas, Cpm minus Cvm is equal to R. Since Cvm equal to 2R, I can write Cpm equal to R plus Cvm. So R plus Cvm value is 2R. So R plus 2R is 3R. This is the value of Cpm. Substitute this value here. Okay, but this is for small change. For finite change, you have to integrate. So integral, okay, integrate both sides. Okay, so integral of N into Cpm into dt. Okay, initial temperature T1, final temperature is T2. Number of mole is constant. Cpm is, listen, if Cvm is independent of temperature, Cpm must also be independent of temperature in the case of ideal gas. Okay, so Cpm is also independent of temperature. Then integral dt is nothing but T, upper limit T2, lower limit T1, so T2 minus T1. This will give you change in enthalpy of the gas. Now, number of moles given as 10 mole. Cpm value, if we found out 3R, 3 into R value is 8.314 into final temperature is 340 and initial temperature is 310. Okay, now, so 10 into 3 is 30 into 8.314 into 30. Okay, if I multiply everything, I'll get the answer directly. Okay, so we get the answer as 7482.6 joules. We get the answer directly in joule because R value is in joule now. Okay, 8.314, right? This is the R value of R. R value is 8.314 joule per Kelvin per mole. Listen, here this is 10 mole. Mole inverse cancel, and this is in Kelvin inverse, and this T2 minus T1 is in Kelvin. Kelvin inverse cancel. So we left with the joule. So this is the change in enthalpy, okay, for the isobaric heating of an ideal gas from 310 Kelvin to 340 Kelvin. Okay, yeah. This is the method to find the enthalpy change whenever isobaric heating is given. Okay, and it is, and keep this also in mind, the gas given is an ideal gas. Okay, take it. Okay, now let's move on to this question. Cp and the Cv values of 10 moles of an ideal gas are measured experimentally. Calculate Cp minus Cv. Okay, you know very well, it is given ideal gas, right? So what is given? Given number of moles is given 10 moles. Okay, 10 moles, and it is given that the gas is an ideal gas. We know very well, for ideal gas, Cp minus Cv equal to N into R. Listen, Cpm minus Cvm equal to R. This is for 1 mole. For N mole of gas, Cp minus Cv equal to Nr. Since in the question they are asking Cp minus Cv, so Cp minus Cv is equal to number of mole is 10, R value is 8.314. Listen, this is in joule. Sorry, this is number of moles. So mole unit. Gas constant unit is joule per Kelvin per mole. So mole per mole cancel. So the final answer is in joule per Kelvin. So if you multiply by 10, I'll get 83.14 joule per Kelvin. Yes, this is the answer for Cp minus Cv. Listen, this is the Cp minus Cv formula for an ideal gas. For N mole of ideal gas. For 1 mole of ideal gas, this is the formula. Okay, and this is also called as a Mayer equation, right? Try to remember this. Right, so this is the next question. An ideal gas undergoes the following process. Calculate the work done. And here in this graph, in the y-axis pressure is given, and in the x-axis volume is given. So it is PV diagram. And see, this is the initial state and this is the final state. Okay, initial to final state, solid line is not given. Okay, no information is given about the path, which means the process is an irreversible process. It is an irreversible process. Okay, now volume informations are given, pressure information is given. So in the initial state, initial volume is 5 liter, V1 is 5 liters, and in the final state volume is 1 liter. Volume is 1 liter. That means compression takes place, compression of gas. In the initial state, pressure is 1 atmosphere, and in the final state, pressure is 5 atmospheres. And you know very well, during the irreversible expansion, okay, the pressure at the final state, is taken as the external pressure. Okay, therefore, work done, the general formula for work done is minus integral V1 to V2 external pressure into change in volume. Now in this case, what is external pressure? Whenever irreversible expansion takes place, the final pressure is taken as the external pressure. Okay, so I'll take the final pressure as external pressure. Now what I'm going to do, you draw a straight line here, draw a straight line and draw a straight line here. This is the initial volume, this final volume, and this area will give the total work done. Okay, because this is the final pressure. So final pressure and the change in volume. Okay, this area will give you the work done. How to find the area? This area, take this difference, you will get this length, and take this length, multiply this into this, you will get the work done. So differences, we can use that idea, or you can also use the formula. Okay, both will give the same answer, minus. So what is the external pressure? The external pressure is nothing but 5 atmosphere. So let me write here, external pressure. In the case of in the case of irreversible process, external pressure is constant. So external pressure is equal to the final pressure, which is actually a constant because the process is irreversible. Since it is a constant, you can keep it out. So P2, okay, then integral dV is V, upper limit V2, lower limit V1, so you'll get V2 minus V1. So minus the value of P2, final pressure is 5 atmospheres, into final volume is 1 liter and initial volume is 5 liters. So 1 minus 5 is minus 4, minus 4 into minus 5, you will get plus 20, and this is in atmosphere and this is in liter, so you will get the answer in liter atmosphere. How to convert liter atmosphere into joule? Just multiply this by 101.3. Okay, so 20 into 101.3 will give me 2226 joule. Okay, this is the work done in this process, right? Remember, in the PV diagram, if the initial to final path is not given, or if it is given in dotted line, then you should take it as an irreversible process. If it is given as a solid line, then it is a reversible process. Okay, keep this in mind.